Hello everyone, so now we're gonna go over division of polynomials. So last week you learned how to add polynomials, how to subtract polynomials, how to multiply. Now we're gonna go over how to divide. And the division is kind of similar to the multiplication process. It's just kind of like going backwards, and then it's also dividing instead of multiplying the numbers and the variables. So step number one is you want to separate all the terms with the denominator. So we know that whenever we're adding or subtracting a fraction, right, we can put all the addition or the subtraction in a one single fraction with one denominator, right? However, we can also separate them, and so each term will have the denominator for itself. So we can rewrite this as 35n squared over 5n squared, and then plus, and then 20n to the fourth power over 5n squared minus 5n over 5n squared. So notice how all of them have the same denominator, because again, this was an addition and subtraction, and they were all in a single fraction with one denominator. So now what we're going to do is we're going to apply division, and we're also going to apply the quotient rule for exponents. So remember, the quotient rule for exponents says that if you have a to the m over a to the n, so as long as you have the same base, then you can go ahead and subtract the exponents, right? And that's what we're going to be playing with on this example. So first, let's see how on the first fraction we have 35, which can be divided by 5, right? On the second fraction, we also have two numerical values that can be divided, so 20 divided by 5. And then on the last one, we have 5 over 5, right? And then we can see that we have n values, right? So on the first fraction, we have n squared over n squared. So we know we can apply the quotient rule for this. And then on the second one, we have n to the fourth power over n to the second power. And then on the last one, we have n over n to the second power. So we can see that we can apply the quotient rule, for exponents. So if we divide 35 by 5, this is going to give us 7. And then we will have n2 minus 2 plus 20 divided by 5 is 4, and then n to the fourth minus 2. And then minus 5 divided by 5 will be 1. I'm not going to go ahead and put the 1. Remember, that can become just invisible because it doesn't really change the value of whatever it's multiplying. So I'm just going to go ahead and write n. Remember, there's an invisible 1 right there, so 1 minus 2. So this will give us 7n to the 0 plus 4n to the second power minus n to the negative 1, right? Now, n to the 0 power, remember, this becomes 1. Anything that has 0 as an exponent becomes 1 automatically. And so I can rewrite this from the highest degree to the lowest with 4n squared plus 7 minus, and then because this is a negative exponent, I'm going to go ahead and write it as 1 over n to the first power, which is 1 over n. And this is the division for this particular example. Now let's go ahead and try a different one. I'm going to go ahead and erase this. Now this next one, it's going to be written a little bit different. But again, it's not going to be written as fraction, but again, it's going to be a division. So it says divide 30z squared plus 3 minus 50 z cubed plus 18z, and then divided by 10z squared. Right? So what I'm going to do is I'm going to write this as a set of different fractions that are being added and subtracted. So I'm going to go ahead and do 30z squared over 10z squared, and then plus 3 over 10z squared, and then minus 50z cubed over 10z squared plus 18z over 10z squared. So this is what I meant when I said that it's really similar to the process of multiplying two polynomials, because whatever it's being divided, it's kind of being distributed to everything, right, on the first parentheses. However, instead of multiplication, we have it as fractions, right, with a division. So in this case, we're going to apply the same rule as in the previous problem, where we can see that the numbers are going to divide with the numerical value, or we can simplify, right, the values that we have in the fractions. So we have that, and then we also see that we have these values with the z, right? So we have the same variable, same base, so that means that we can apply the quotient rule again. So for the first fraction, we have 30 divided by 10. That's going to be 3. And then we have z squared minus 2. And then plus 3 over 10 cannot be reduced, so that's going to stay as 3 over 10. And then we don't have any z value on the top, right? So we're just going to keep the z squared on the bottom with the 10. Minus 50 over 10, that's going to be 5. And then z3 minus 2 plus 18 over 10, it can be reduced by 2, which is going to give us 9 over 5. And then z, again, remember there's an invisible 1 right there, so 1 minus 2. So this is going to give us 3z to the 0 power plus 3 over 10 z squared minus 5z to the first power, 3 minus 2 is 1, plus 9 over 5 z to the negative 1. So we know that this z to the 0 power becomes 1, so this is 3 times 1. And then plus 3 over 10 z minus 5z plus 9 over 5, and then this z to the negative first power, it's going to come down with the 5. So it will become 9 over 5z. So when I write the polynomial from highest to lowest degree, I'm going to begin with negative 5z plus 3 times 1, which is 3, plus 3 over 10, I'm sorry, that will be plus 9 over 5 z. Reason being, it was only a 1 in the exponent on the bottom. So the bigger the exponent in the denominator, then that means that the lowest the exponent. So this will be 9 over 5 z, and then plus 3 over 10 z squared. So again, the higher the number in the exponent of the denominator, of any base in the denominator, that means that the lowest the power is going to be. Okay, so the higher the exponent in the denominator, the lower the value of the entire base, or the entire term. And this is it for this problem.